Well, last time we had finished the idea of the generation of an action potential. We'd gotten as far as producing an action potential. We talked about the different kinds of channels. We had talked about the idea that we opened voltage-gated sodium channels followed by voltage-gated potassium channels, and at the very end we invoked the idea of the voltage-gated potassium channel being responsible for rapidly bringing the membrane potential from near the equilibrium potential for sodium back down close to the equilibrium potential for potassium. We're going to take that up again today, and I'll walk you through some slides because it's such a fundamental idea that we need to be very clear about it. The other piece that I in fact got to in the second section, but I didn't get to in here, and I'll try to bring it up as we move through it, but the major idea that you really need to hold on to that comes from this movement of charge across membranes is that the number of charges that move to generate an action potential, that we can shift the potential from, say, minus 80 millivolts to up around plus 50 millivolts. We can get that 120, 130 millivolt excursion by moving a fairly small number of ions. The number of ions that move in a typical action potential may be no more than a few million. That sounds like a big number, but in fact it changes the intracellular concentration of sodium, which is normally in the 10 to 15 millimolar range, from about 10 to 15 millimolar to about 10.00001 millimolar. It doesn't change it very much at all. And so when you begin to recognize that, then you see that at the end of the action potential, you've hardly changed the concentration of sodium on the inside of the cell. That means then the only charge carrier available to use to work down the concentration gradient is for potassium now to leave down the concentration gradient, to move through those voltage-gated potassium channels, and to then bring potassium or positive charge out of the cell. What we're going to do today, though, is all of that was emphasizing the cycle, sodium in, potassium out. It said very little about carrying information over long distances, and yet we'd emphasized the concept that where we find these voltage-gated channels is along the conductal region of neurons. And so what we want to think about here in 3 steps is how we manage to get action potentials to move along the membrane. The first case is pretty much a thought experiment, although this idea, this concept is going to come back again when we talk about the input regions, when we talk about synapses. But in this first sort of thought experiment, we're going to put the voltage-gated channels only at one place. We'll imagine generated action potential, but then the rest of the membrane will be characterized by a lack of voltage-gated channels. We'll have leak channels, but no voltage-gated channels. What this brings up then is the idea that the leak channels will carry positive charge out of the cell. And it means that if we have voltage-gated channels at one place, but the remainder of the membrane is occupied only by leak channels, then the potential is going to get smaller and smaller. This is the concept of the decrementing potential. The potentials will propagate along membranes lacking voltage-gated channels no more than a millimeter or 2. So to get long-distance propagation of these potentials, we then have to invoke a continuous layer of these voltage-gated channels. Or to invoke the idea that one voltage-gated channel supplies positive charge that opens the next one, and like a series of dominoes, propagates the potential along the membrane. And we'll talk about this. In the first iteration, we'll talk about propagating potentials that lack myelin, but contain numerous voltage-gated sodium and potassium channels. These axons, and they're quite common in our bodies, these guys will propagate potentials at a slow rate, about 1 to 2 meters per second. 1 to 2 meters per second really isn't fast enough to do a lot of the things we need to do to keep our lives functioning. And so then we have to think about how do we manage to get faster conduction velocities? How do we manage to move this information from one part of a neuron to another at much, much more rapid, much faster action potential propagations? And we do this by myelin. Remember we talked about the oligodendrocytes and we talked about the Schwann cells. We said that we wrap those insulating layers around axons, around the conductal regions. Well, we'll see this again. We'll lay this out again anatomically, morphologically, and then we'll emphasize how that morphology then comes round to allowing a much more rapid conduction of action potentials, up to over 100 meters per second, simply by wrapping the so-called internodal regions in those myelin sheaths. Well, all of that is about moving potentials over long distances, but it says very little about how we initiate the original influx of positive charge. And this is a question that comes up over and over again. Where does the positive charge come from to initially open the voltage-gated sodium channels? And now we're going to initiate that idea here. We're going to initiate this idea with something called a generator potential, and we'll use, as an example of the generator potential, the stretch-activated channels that you can imagine being located out in one of your touch-sensitive neurons out in the tip of your skin. And we'll talk about the idea of opening these stretch-activated channels. And as we go through this, one of the ideas you need to hold on to and recognize as we move through this is that we have two very different kinds of channels. We have voltage-gated channels that open in response to charge. They're clustered in such a way that the opening of some of these channels leads to a kind of explosive opening of all of the neighboring channels. So we now end up with a sudden opening of all of the channels at one time. These are different. In this case, these channels open in response to the strength of the stimulus. The stronger the stimulus strength, the greater the response. Whereas the voltage-gated channels are all or none. You reach threshold fired action potential, you're there or you're not. Here we can grade, we can regulate, we can change the amplitude of the potential over a broad range by changing the number of channels that open. So now we have a kind of analog signal here, which can now then lead to the opening of voltage-gated channels opening. So we go from a kind of analog signal, which is graded with the strength of the stimulus, to one where we open these channels, reaching threshold to drive the membrane potential to threshold to begin the propagation for an action potential. So if there's time, we'll try to bring this idea full circle.